Uh, Hello and welcome to this week's Graphics Programming Weekly. We're going to be covering Chapter 5 of Vulkan Guide. It's all about textures. So at first we have to cover a bit about memory transfers. Let's get started. In brief, a VK image is another storage target for memory in Vulkan, like a VK buffer. However, it has a whole lot more state and stuff associated with it, so much so that it's actually accurate to describe a VK image as just a fancy VK buffer that's built into the API so it can take advantage of hardware acceleration where possible. So we're going to be doing a whole lot of stuff to get an image and to use an image and to draw an image this chapter, but you could conceptually implement all of that stuff using shader and other tricks. It's just wouldn't be very fast and you wouldn't have access to the fast stuff on the GPU. So that's why we want to use all the kind of difficult and clunky looking image stuff. Before we can get into that topic though, we do need to discuss in relative briefness memory transfers, specifically staging buffers. Right now, we've been creating our meshes in the CPU to GPU memory type, which this is a Vulkan memory allocator abstraction. The better name for it probably is host visible / device local memory. We don't really want to be doing that on a dedicated GPU because that is going to be living in a memory region that's accessible both by the CPU and GPU. The reason we did that is because we can write to it from the CPU, which makes it easy to load the mesh from the hard disk and then write the mesh data into the buffer, the VK buffer. To be able to move memory into GPU only, or otherwise known as device local only, we need a staging buffer, which is a VK buffer in the host visible device local that we then issue a command copy buffer. Actually not device local, just host visible. So this is conceptually a CPU buffer that the GPU can, well, the DMA engine can read from. So this is a nice graphic I found. What we're doing right now is the bottom, so ignore the arrow here. Buffer raw data, mem copy into a VK buffer. What we want to be doing is buffer raw data, copy into a staging buffer, record and execute a command buffer that copies that data from the staging buffer into the VK buffer. So essentially there's two mem copies, but one of them is happening from CPU RAM to GPU VRAM. That's what we're going to be doing this chapter. We're going to be abstracting it so that we can upload images as well as buffers. Well, we're going to start with buffers just for simplicity. One last note, if you're working on a unified memory architecture, this kind of staging buffer nonsense is actually somewhat unnecessary because unified memory architectures are things like Intel integrated graphics, mobile GPUs, where there's only one space of memory. There is no dedicated VRAM that's its own distinct thing. I think consoles like Xbox and PlayStation fall into the unified memory architecture. I could be wrong about that though. VMA, someone asked if VMA automates staging buffers. The answer is no, it does not. It makes it easier to use because you can use the CPU to GPU and GPU only memory type tags to simplify the allocation and creation. It does not like make it a one function call kind of thing. So we're gonna try to blaze through the edits we're gonna make. We're gonna make a new structure called the upload context in the engine, and it will be the stuff we need to execute a memory transfer. Memory transfers In our case, we're just going to execute the transfer, wait for the transfer to finish, and then continue. In a big fancy engine where we could create mechanisms to run this in the background, and we can see how it happens in the future, but we're going to go with this is the simple implementation, and it makes it easier to explain. So I just added the function immediate submit. It takes a function by parameter. So in C++, we have the std function type, which has a template argument, and we're going to templatize it on another function. Not another function, but a function. And that function is going to return void and take a command buffer by value. This allows us to create a command buffer in the immediate submit function, pass it into the function that was passed in, and call it, and then execute that command buffer. You'll see how it works in a second. We need a fence and a command buffer and a command pool. So we're going to create those things in the appropriate places. Let's go to init sync structures. Does this work? Yes, it does. So create a fence. We're not going to create it as signaled because it starts life as unsignaled because we need to wait for it to finish. And it just doesn't make any sense since we're not using it every frame. We're only using it at startup. Similarly, we need a command buffer, and it's somewhere here. I create that. Yeah, here. But to create a command buffer, we need a command pool. So we create a command pool. Do we have any special flags for it? No, not really. That's actually fine. So we can copy the big block of code that I will walk through and try to dissect. So this is the function. The ampersand here does not mean logical and, it means R value reference. I think that is perfectly fine code. And actually, I kind of want to do that because that's simpler to understand. It's just passing a function by value, or a function template type thing. Oh, okay. So maybe I do need it, but as discussion in the comments say, but this is special C++ syntax that doesn't really affect what we're trying to do here in detail. We have to, because we want to create a command buffer, we're going to allocate one from the command pool. And at the end, we're going to reset the command pool, which returns the command buffer. And then we don't have to actually, does this free the command buffer? I am actually blanking. So, I think that's wrong. It doesn't free the command buffer, it just resets it. So I think this actually, leaks a command buffer. I will have to investigate it later.
The line before the one you highlighted seems to suggest, with the word recycled, that the resources in the command buffers are freed, but it doesn't explicitly say that.
So,
it says, yeah.
I think this is necessary to make it free the command buffer. So this actually might be a bug that is latent and kind of, because this is only called in setup, it's not really a big issue. It's not going to leak and leak and leak. It's going to leak once and that's it. But that's a tangent. We allocate a command buffer, we begin it, and we record by calling the function and passing in the command buffer we just allocated and begun. Then we end the command buffer and it is ready for submission. And we get our submit info using a helper here. We're not going to use any fences here. I meant to say semaphores. all we're going to do is a single command. If we look at the implementation of this, it just does the single command here, passes in it. So that's a little helper. We submit the queue with our upload fence, then we wait for the fence to finish and we reset the fence so that we can call the immediate submit again. And then reset the pool with this flag to clear the command buffer. I think the solution to this problem is actually quite simple. We just put this here and wait, this is live coding with Charles. Where is it? We take this, we throw it in here. I guess I need that. And we do upload context. Okay. Okay, I think this is correct now. Oh boy. So, and then we can remove this stuff here. So we allocate it at the start and then we just reset it after we're done using it. So I'm going to have to do upload context dot. Okay. So that was what we do to upload stuff to the GPU. Specifically, we need this as a skeletal structure. The actual copying will be done in this function that we have to define later in our function upload. Now we're going to replace our upload mesh function with that. And I believe I can just delete all this and it's unnecessary. I'm going to comment it out for now. We have to create a local buffer to store the memory in on the CPU. So we have a buffer whose size we get from the mesh that we've loaded already. And we're going to use it as the source for a transfer. So the only usage thing we need to provide is the transfer source bit. Since it's a staging buffer, we have CPU only, guarantees host visible and host coherent. So this is some of the actual technical details of what that means, and you can read it at your own leisure. So we create a buffer, and we've created it, but now we need to copy the data in. This is what the Mem Copy and Unmap does. So after this line, so at this point where I have the silliness that is me spamming keys on the keyboard, at this point in the function, the buffer on the VK buffer on the CPU, the staging buffer, contains the data we want. Now we can go ahead and create the GPU buffer. And as you notice here, we have the usage of vertex buffer and transfer destination. So this will be where we write our data to, not where we read it from, same as size. And here we have GPU only because it's going to be GPU only that we're going to be using this memory. Similar VMA create buffer call. And now we get to the fun bit. So to break this apart a bit, we have a lambda here, which is just a function defined inline without a name. It takes command buffer as parameter and defines a buffer copy struct, which gets used in the command copy buffer. This is the signifier that the lambda should copy any local values it references. So staging buffer and mesh vertex buffer.buffer, those both get copied. So it's kind of like we did an implicit thing here. This is the list in between the square brackets is the capture list. So it's the list of local variables in which to capture and we want to capture by value, meaning we're going to copy the data. Because we want to do it automatically, because we're lazy, we're just going to use the equal sign. I feel like I've explained this before in the other thing, in another chapter, but regardless, we pass this lambda into the immediate submit function. And so we don't execute this before we call the function. We just pass the function in so that the immediate submit function can call it when it wants. And as if I hit F12, we should see we pass the function in, it does all the setup, it calls function, which will go back to where we just were, which I don't remember where that was. Yeah, here, it call these lines of code here, and then return execution back to this point, end the buffer, submit, wait, and when this function exits, the buffer will have been transferred, and we can be sure that the buffer has finished transferring because we waited on the fence associated with the submit. So now we just need to clean up our temporary buffer, the staging buffer, and push. I'm going to move this down because I think this should. Yeah, we destroy the temporary buffer, and then we push the deletion of the main buffer to the main delete queue, so it happens at shutdown time. Lambdas allow you to do fun stuff, and we'll use this to great effect for the image copying later. Now we can get to actual images. Hopefully that didn't take too long. A VK image is the main type that stores the data, but an image view is a way we can access it. It stores some information about which layer or the regions of the image to access. There is also a sampler. If a layout is what region of memory to access, then a sampler is how we access it. A sampler is divorced from the image handle, and that's very nice because we can reuse samplers. You could also just create a sampler on the fly and it'd probably be fine. But for a pure API standpoint, a sampler is its own distinct object, and we'll have to create all of the three of these things if we want to be able to use an image in our normal rendering. We will be using VMA allocator to allocate the memory for the VK image, but the image view and sampler are both going to have to be created manually. We want our images to be read by shaders on the GPU, and we want those reads to be as fast as possible. Therefore, we want to put our images in device local memory, or GPU only, as VMA calls it. This means reads go directly to VRAM. They don't go to CPU RAM or any other weird place. This will require us to transfer the images using a staging buffer, which is what we just set up last chapter. Images have a format and a layout. A format is the description of the pixel arrangement. Let me go, can I just create a new thing? Oh, where's Notepad? There we go. So pixel encoding, language C. So a pixel, the format of the image can be kind of described as how each pixel is arranged in memory. So a classic RGBA pixel would be like this, where each color channel gets 8 bits, so 1 byte, and there's an alpha channel and it's arranged like this. And this would be called VK format R8, G8, B8, A8. Is this the format name? Oh, it's in the next chapter where the code is. So I'd have to Oh, sRGB. And then there's the color space. So this is how you interpret the values. sRGB colors versus unorm, which is normalized but unsigned. So these, actually you could char would be appropriate here too. Anyways, there's other layouts. I mean, there's ones with 16 bits per pixel, and that would be something like this. And its size would be 64. Wait, no, this is 32 bits. So this would be 64 bits. So it takes up a whole lot more memory bits. There's funky layouts, which are like this and have no alpha channel. And these are like for HDR stuff. And this is a 32-bit layout, but 10 bits are for the red channel, 12 bits are for the green channel, 10 bits are for blue channel. There's others that have, I'm just int2t, which is not a real C++ type, but that's okay. There's a whole lot of formats, and they describe how the individual values in the pixel are arranged. But the layout of an image is vastly different because it is an implementation detail and not something that can be understood from reading the API. Like, okay, this description of a layout maps very well to a struct definition. The description of a layout is not so kind. So if we go to just layout. Where's image layout, shader read-only optimal? That's the kind of thing I'm looking for. No, yeah, here. These are the different image layouts. Color attachment optimal, depth stencil attachment optimal, read-only optimal, shader, transfer source, transfer destination. All of these formats might mean something to the driver and refer to how the pixels are laid out in memory. So Z order curve. One of the things that layout has to do with is how the pixels are arranged in memory. They could be using a Z order curve or Morton encoding, all sorts of fancy things. But the point is that the format is understandable. The layout is just a name that you know what its intention is, but there's no intuitive way to figure out what that means byte for byte. Like you can't just, well, actually, if you go to the open source drivers, then you could do that. But I digress. So Imageview is a view onto the image. We'll see more about it. Stuff like bitmaps, levels, and other stuff we can specify in it. And that's useful, but for what we're using, we're going to use a whole image view. A sampler I've already touched on. You don't create a sampler with a VK image. You just need one to use the VK image, so you end up creating them at the same time. In our shader, we're going to use combined image sampler. What that does is it combines a VK image view and a VK sampler into a single thingy that gets uploaded to the GPU. This is kind of how OpenGL did things, from my understanding, where each OpenGL image always had its own sampler, even if it was the same sampler or shared across many hundreds of images. So let's see about actually loading some images. We will create two new files, VK image and vktextures.h and vktextures.cpp. I've already taken the liberty of creating those files because that would save me some trouble dealing with CMake, having to rerun it and all that. We'll define a function called load image from file. This is like load mesh, but it uses different things because it's loading an image and not a OBJ file. I mean, it's, what are you, that's what you were complaining about. It's like this function, but for textures. So We use the STBI library. It's very easy to use. We are loading a RGBA, so alpha is the A, image, and loading it into this pixels buffer. We want to calculate the size of the buffer in GPU memory terms, and that's going to be our width, our height, times the size of our pixel, which is 4 because it's 32 bits or 4 bytes. And we're going to specify the image as just that same thing, but with our VK format. And we're going to create a buffer given those parameters. Oh, why does it? Oh, I remember. Private. Wait. That was the wrong one. I remember. Okay. This is something that I forgot about. Okay. So we create a buffer with the transfer source usage bit, and it's CPU only. So it's just a same thing as we were doing in the previous chapter, but we're going to use the image size because we're allocating image. Then we copy the data into that image. We can map, mem copy, unmap. No, don't do that. And then now that we've copied it into our own local buffer, we can free the pixel data in that CPU buffer. So there's really 2 CPU buffers. I feel like there's a way to get around having a separate CPU buffer, but I don't know how to do that off the top of my head. And it's only in startup, so it's not that big a deal. Plus you can reuse memory and other things like that if you want to get performance sensitive. So now we need to do an image transfer, which is a bit more involved than the buffer transfer. We first need to create the image, and we'll specify a few more things than what is necessary to create a buffer, such as an image extent. So the width and height and depth, the width and the height are the width and height, and their depth is 1 because it's a 2D image, not a 3D image. Our image create info, it has several arguments. We have our format, the sRGB, the RGB, R8G8BA8 sRGB. That's our format we're going to use. Sample transfer because we're sampling. Yeah, this is the actual VK image. Can I get this? Yes. We're actually allocating the image that we want to, because we allocated the CPU one up here. The GPU image will be used as a sampled image. It will be read from, but it will also be written to in an upload. So that's why it's a transfer destination bit. And the extent is, it's the extent. We use VMA to create the image, and it goes and allocates in the memory and does all the heavy lifting for us. And so now we get to the fun bit of the upload. So we have our immediate submit function again. And this time we're passing by reference, which is interesting. So this ampersand means don't copy the value, copy a pointer to the objects. So this actually has slightly different semantics than this, but I'll leave it as is. What was the reason why we needed the barrier? Okay. So images have a layout, and we can change what layout that image lives in. However, that is an explicit operation that we must perform. And the way we perform it is using a memory barrier. So we have to execute, and a command pipeline barrier is how we issue memory barriers. This tells the GPU that we want to transition the image from this layout to this layout, undefined to transfer destination optimal, because we want it to be in the best layout for accepting data from the CPU. I failed to mention that images start life as undefined layout. That's a very important thing to have said, but I will have said it now, so that's good. We can see our old layout and our new layout. We have to specify which image we want, and then the sub-resource range is which part of the image we're referring to. And this is useful if we will have different parts of the image and different I don't say layouts, but different things. When people talk about Vulkan being an explicit API, this is the kind of, including the pipeline barrier, this is the kind of thing that makes it explicit. You have to explicitly change the layout of images. And this is something that render passes did for us, and it kind of did it covertly and not obvious. So I appreciate having to showcase it directly because it makes it clear that we need to do it. Source access mask, and this, I don't know if I can explain it that well. It's really saying what part of the memory to worry about. Memory barriers are just poorly explained in general, and I do not have the gusto to try to explain them to y'all. So this function, oh, we need to continue. We're not finished copying it because we didn't actually issue the copy yet. So this chunk of code moves the image from undefined to transfer destination optimal layout. Now we can issue the copy, and we do that by filling out a buffer image copy. Note that we actually create a buffer on the CPU, not an image. Since we're not sampling the image on the CPU, there's no real reason to create it as an image. In fact, it's much simpler if we just create a buffer and store the image data into it. It's explicitly supported by the API thanks to functions like copy buffer to image. So we specify our staging buffer and our destination image, and it will do the copy and fill in the pixels from the staging buffer into the VK image as dictated by the, well, GPU, how it wants it to be done. We have to specify our things. We don't have any offset or things here. It's been a while since I've looked at these because these kinds of structs are ones you abstract away and then you forget about because you don't interact with them on a daily basis. And so I'm like, wait, what does this do again? So this is what we specify, and then we have our command to actually execute it. What was that argument? That one? Yeah, this is the image layout that we're doing it. So this is the same as this here. And it's just saying what layout to move it into. Now that we've copied the image, we have to transform the image once again from the layout of transfer destination optimal to shader read-only optimal, which means optimized for reading the data. I'm going to put this extra space in here. So we have another image barrier. Now we have old layout and new layout from the transfer dest optimal to shader read-only optimal, and after this completes, it will be in the format we want for us to read it in the shader. Again, we need to clean up stuff and finish up our function. So we create a new image. We want to destroy it at shutdown, so we push it onto the deletion queue, and then we destroy the staging buffer, and we print out a message saying we're done. And I can delete that line. We just assign the image that we've created, and we're one chap. Oh, there's still stuff to do. Whoops, I thought we were done with this section. Okay, we actually need to call the code we just created. We're going to create a new struct for holding the texture, so the allocated image, the image view, and we're going to have a hash map of textures. So this will be like our hash map of materials and meshes, but it'll be for textures. And we'll want to load all the textures at startup. And we'll go up here and call our function before we initialize the scene, but not before we initialize our descriptors. Okay, that's annoying me that they're not in the same order, but I'll have to ignore that for now. Okay, so we copy the function, the load images function. We have to include the header that we just created. Where is the other stuff? It'll be fine here. Okay. And we can look at what this function is doing for us, and it's using all of the code we just wrote. We have our image, load image from file. Why is it? Okay. And then this will be our destination where we write the image to, and now we create an image view from it. We'll use a image view create info helper that we did before, and it's basically respecifying all the same information we did before. We have our format, we have the image, the actual VK image handle. We'll have our aspect, which is the thing we're using it for, which is colors. We're using this image view to do color stuff, so we'll do that. And then we add our texture to the texture list with this name to it. And if I hit F5, it should compile and run. Be a good time to do it now in case I mucked something up. What? Oh, I copied that twice. Okay. Okay. So that says we forgot to clean up something, but that's okay. I don't care. Now we can actually get on to using the image and get on over with. If you're not familiar with what a UV coordinate is, I don't know how to tell you how to describe it other than it's like origami, where you take a 2D piece of paper and you fold it up and turn it into a 3D shape. The UV coordinate specifies the location on a piece of paper, and each vertex knows its UV coordinate so it can figure out where in a 2D image to sample from. Yeah, someone asks, it's the mapping, or someone says it's the mapping of a 3D surface to a 2D surface. And yes, the UV coordinate is how we handle that. If we look at our meshes that have textures on them, every vertice will have a UV coordinate, and that's the mapping of a, like, to put it another way, it's the position in 3D. It's that UV 2D. Ignore the warnings, but we take the 3D position, and now we know where in the 2D plane of the texture to look for the color data. There are better explanations of it, but this tutorial is not that tutorial, and so I heed y'all to go look it up on your own. Because we're changing the description of a vertex, okay, I've been corrected. Projection is how we map 3D geometry to 2D screen. Okay, it's a fair point. It actually is pretty important to understand, but this tutorial doesn't go over it, so I'm not going to go over it. We need to update the description of the vertex because the tutorial does. And so we'll change this to include a new vertex attribute description. The notable thing is that it's a different size. It's at the third location, but its size is 2 32-bit integers. And we just add our description to our list here, and this basically finishes updating it, and it's good to go. We do need to pull the UV data out of the OBJ model, which is here, and we can just copy paste, UV, because that's actually a good question, why this is here. This is implying that the UV coordinate is in the wrong axis, and we have to invert it. So instead of being top down, it's bottom up, and we have to invert it here. I'm not sure exactly why that's needed, where in the pipeline that happens, but it happens here, so hopefully it's correct. Vulkan's coordinate system is different than OpenGL and is different than DirectX, all the other APIs. Okay, we're going to create a new shader based off the, no, we're not going to create a new shader just yet. We're going to modify our triangle mesh vertex shader to have the UV in its description. So we're adding it there. Because our texture coordinate is used in the fragment shader, while we describe it in the vertex shader, all we're going to do is pass it through. This happens to interpolate the values across the triangle. And now we can get to our actual fragment shader that we want to write. We're supposed to copy the, oh no, we already created this one in the previous chapter. Did we? Yeah, we created a new one. Okay. It's always confusing, and I've already copied it because I prepared it a little bit. So this is the line where we take our X and Y coordinate of the texture, and instead of passing them directly, okay, where is that? Instead of passing it directly, we're going to sample from a texture that we're going to pass in as a descriptor. So instead of creating the color from the value, the UV values directly, we're going to use those values to sample a texture, and this will get us an RGB color that we can use like so to do our final output. Seems like I need to go and fix up the pipelines to load this new shader that we have created. So I'll go do that. This is where the tutorial kind of lost me at times, and I had to refer to the final version of it, which if you go to the code and you go to the all chapters branch, let me go here and I'll just copy paste this. Actually, yeah. So if you want to see what the final working code looks like, this is the place to look. And I found it very helpful because the tutorial was sometimes a bit mucky in how it described everything. Where is init? Oh, init pipelines. Okay, here we go. So I'm going to copy paste, create a new textured mesh shader module. I think we already have that. Build a mesh pipeline. We're going to create a new pipeline for our textured stuff. So we need to clear out the shaders we use, our mesh and our textured. This is wrong. This is something I complained about. And that's one of the reasons I was annoyed with the tutorial, is that the tutorial text is inconsistent and incorrect. But we can go to our thing here, and I'm actually going to unload these things by commenting them and then load our Lost Empire, which is the Minecraft map, which is illustrated here. Where was I? Oh, here. And instead of drawing triangles, we're gonna just comment that out, and we'll get the mesh from the Empire. We'll have a material textured mesh, which is loaded in the init pipelines, and we just translate it a little bit and then push our renderable. So we'll only have one renderable, but it'll be the entire Minecraft map. So the hotkey, that comments code, is Control K, Control C. And the hotkey that uncommons code is Control K, Control U. So if you look at the bottom of the screen, you'll see that Control K was pressed, and I do Control C, and yeah. I don't know why it does double lines here versus oh, if I select it, weird. Oh, anyways, yeah, someone was asking how I was commenting code so quickly. Okay, we have our material, single texture. We need to create a descriptor set layout. This is one of those things where I'm just kind of following the tutorial because I've covered all the salient, interesting bits, and I just want to show off what it looks like at the very end. Where do I throw this? Here. Yeah, it's the plumbing of this all. So we have, do I need to update that? Yes, I do. So a material will have a image as well. So a descriptor set that contains an image, and we'll put it in its own descriptor set. I think that's everything. Okay. So in init descriptors, we need to expand the size of our pool because we want combined image sampler descriptors to be in the pool for us to create descriptors from. Since we have to allocate the pool with a fixed size of objects, we need to make it as big as we need. Then we'll create the descriptor set layout we need, which actually is here. So this will be our layout for the sampler. So the layout binding, combined image sampler, only available in the Fragment Shader. We only have one binding because we only have one image. If you had multiple images, you might have multiple bindings. That'd actually be a decent thing to do. If we wanted to have multiple images, this would be more or less what it looks like. And so you'd have 4 images here. Say this is your albedo, this is your metal, this is your normal map, this is, I don't know, a emissive, whatever, you know, a bunch of textures. And then in your, I'm going on a tangent and I will delete this code in a second. There'd be only one descriptor set, but here we'd have four bindings, and then we describe the array of bindings. So we'd have, you know, an array of these things. Someone, let me relook at this. So we are using a separate descriptor set for the texture. And in my hypothetical, I had textures because the texture is really associated with the material, whereas the object we're rendering is different. Actually, this is all the object data in a single buffer. So this is actually kind of different because we upload all of the objects data at once into a single buffer, and we only have to bind it once. But each material is going to have its own texture, so we need in a separate descriptor set. So we only bind that single descriptor set at a time, i.e. each texture, or, well, textures if we're doing this. So, yeah. Very good question, actually. I'll leave it like that. Go back to our pipeline and continue futzing around with it, getting it working. So this will be the textured mesh pipeline / material. A pipeline is, wait. Okay, now I'm confused. Is this the same as that? Do I need to, did I just copy a whole bunch of stuff unnecessarily? Maybe. Oh, it has 3 descriptor sets, so that might be what's missing. So I'm gonna. Oh, okay. This is the pipeline layout, and that's confusing me. So this is the stuff to create a pipeline layout, whereas the other pipeline layout is created up here. That's what was confusing me. The organization is kind of scuffed, if you ask me. There's 3 descriptor sets in this pipeline. As we can see, there's 0, 1, and 2. So we have to provide the layout for all 3. We set the size and the pointer to them, and we create the layout. Now we can create the, jumped ahead, the pipeline itself. We clear out the shaders. We use the texture mesh, which actually I think I can delete that. Yeah, because that was used earlier, and okay. Yeah, I think that's correct. Compiling it will probably yell at us. So okay. We use the mesh shader and the textured mesh shader for the fragment shader. That's a whole lot of things wrong, and that's because I didn't bind them. Go away. We're not finished yet. We actually don't have the proper cleanup here, but I'm ignoring it because the tutorial ignores it, and it's okay because we don't need to do it. I did this helper stuff before. This is the code necessary to create a sampler. Sampler create info. We have the minimum and magnification filter. That's just passed in. Sampler. This is a whole lot of stuff that, does he go into? I don't think he actually goes into in the previous chapter. I'm going to commit heresy and go to the this tutorial, because this actually explains what the samplers do with good visuals. So we have, this is linear filtering? No, nearest neighbor filtering. So if you have a low resolution image, but you have if you're zoomed in on it, each pixel, like if I do this on it, the pixels across here have to have some sort of value. What that value is depends on the filtering mode. Bilinear filtering will average out the values between the pixels. So we can see that it's, squarish pixels here because the averaging out has corners in them. But over here with the no filtering or the nearest neighbor, it just picks whatever the closest pixel is and has very harsh boundaries. Let me post the link here. So anisotropic filtering is another thing, and it has some performance differences. The addressing mode, this is actually kind of useful to know because it is important depending on the context of what you're doing with the texture. Clamp to border means any sample. Okay. If your image is a square and the top left corner is address 00 and the bottom right corner is address 11, the decimal value of 0.5, 0.5 is the nose right here. If you happened to try to sample address 2, 3, the value you get depends on the addressing mode. In clamp to border, you're going to get black. The only values, you only get non-black value. I think it's non-black values. If the address is within the image. Clamp to edge means it just repeats whatever the edge color is. Mirrored repeat is kind of an interesting one, but repeat just, repeats the image over. So if you sample at position 4, 5, way down here, it actually subtracts the number of times. It turns it into a sample inside the rectangle. and it just repeats it infinitely. This is useful for repeating terrain textures, as I found out. This was actually kind of like a really big revelation. It's like, how do I get terrain textures that smoothly repeats? And it's like, oh, you use the repeat one. And you use a UV coordinate that goes from 1, 2, 3, 4, 5, 6. Okay, I'm going into detail. The tutorial doesn't because I felt it was necessary. And we're almost done. So we need to create the sampler, which we will do in the init descriptors function. Let me move that over. Okay, come on. At this point, I am just copying code. I'm going to do it at the top because I don't feel like thinking about it. So to create the material, to create the descriptor set, we get the material, which means we have access to the texture and stuff. Or actually, no, we have a place to assign it, and we allocate our descriptor set. Then we write into it the data we want. Note the sampler we created, because we're using the combined image sampler, we need to provide a sampler and the image view and the layout we're going to use with it. So our image view comes from our material, which we got up here, and we created the image view when we created the image. So that's what there is. Because we're doing Minecraft, we're actually going to be using the, where was it? Nearest sampler mode. Oh, I passed it. Yeah, this is the look we want because it's Minecraft, not this one. In most hyper realistic video games, you'll actually want bilinear or even a different kind of nicer looking filtering, not the nearest neighbor. But I digress. Last thing we need, we just need to bind the texture descriptor in our draw function, which is somewhere around here. And we only bind it if it has a texture descriptor. Not all our materials do, but the ones that do, we do. So we want to do that. And if I hit F5, I bet there's a compile error. Ooh, it's not a compile error, it's a runtime error. It says access violation. So, what? Oh, we haven't loaded our textures yet. So I think I just need to do this, and that should fix it. That bug, at least. Nope. What is, yeah, this is live debugging. Okay, let's see what it says. Allocate descriptor sets. Oh, okay. Oh, p descriptor sets as null? What? If one of you spot the error, please speak up. Oh. Yeah, it's a null pointer. Okay. It's a null pointer to reference. There's your problem. So do I do this? Where is this code going? Oh, I misread the code so badly. I think I found my problem. I put the code in the wrong place. Yeah. I completely agree. Now where is init scene? Init, nope. Init scene. It helps to read. Okay. There, that's where that code should be. So if I look for that code elsewhere, I will delete it because it's actually wrong. Yeah, this is really unclean. That's happening in the init scene, but it's kind of a consequence. Okay, does it work now? No. What? Okay. What I'm going to do is debug it live by going to the breakpoint. Wrong. Oh, this is the right one. So, one of the best things I found for debugging validation errors is to set a breakpoint in the debug callback. In VK Bootstrap, the default debug callback is what you're using in the tutorial. It's in vkbootstrap.cpp. A more recent version of VK Bootstrap will have it in the header file directly. So it actually is a little easier to find, but we should be able to run it and get hit on the breakpoint as we hit it. And if we look here, we'll see the actual message, but then we can go to the call stack and see exactly when this happened. So it's this call is wrong. And it's saying descriptor type, S type, does it? Create descriptor set layout. P bindings. Oh, okay, this. What does this require? What is the binding? That's right. So type, stage flags.
You check the chat.
Binding count 4. Oh. Okay.
Oh,
so
that's for the example you were making.
Yeah, that's okay. That's called a self-inflicted wound. This should have been 1. I changed it to 4 earlier, so I am a big dum-dum. So I'm going to disable the breakpoint and hope it works this time instead of crashing. Oh, yay! Thank you, Tarun, for catching that mistake. So, okay, any questions, concerns, comments? If I had done my homework, I would have the camera moving around it so I could use arrow keys to explore this cave system.
Whoa, it's Minecraft.
Yeah.
But in Vulkan.
If you want homework, not that I generally want it, but a thing to implement would be fancy lighting, where the torches create light or there's a global sun, because this is unlit. There's no lighting information. Like there kind of is, but it's really hacky global. It's like sun. So actually that would be a thing. So getting this hooked up and making it use of it would be a thing that I would suggest doing on your own. And I think that will do it unless there are questions. So thanks for watching, and yeah, thank you for listening.